Hi everyone, I'm going to go through the Olympiad lessons on gravitation today, and we're going to go through quite a bit of things. We're going to go through the section of forces, and then we're going to go through the section on energy, and then we're going to go through the section on motion in gravitational field. So let's start off with something that you know about up till now. You have done topic 6, so you should know that if you've got an object over here, a planet, and then you have a small little mass over here, this is big mass m, and this is distance r. The gravitational force between them is this. Do keep in mind that r has to always be the distance between the center of masses of the two objects. So this is simple, and we made an assumption that this is a small little object experiencing the gravitational force due to a bigger object. The question is, how do we handle questions like this? Say for example, you've got a mass, big M, you got radius r, you got another rod placed at distance r, we're not drawn to scale, and it has length L. We know that the gravitational force on the object actually decreases with distance. So how do you account for the sum of the gravitational forces at different points due to the planet? So you have to do integration, and this is what I'm going to go through with you, the steps of going through integration, the science and math of this question. Now let's take a look at this method. If you've got a mass m over here, you've got a rod positioned at distance r, we consider the force on this small little section over here. Now this section has a mass dx, and we let rho to be equals to the mass per length. So therefore what we have over here is that dm, the small little mass over there, has a mass of rho dx. And hence what we have here will be that the small little force on this small little mass will therefore be dF, that small little force, is equals to g big M small little mass upon r square. This r square, you have to be very careful. Probably I write this as big R so that it is not mistaken as this small r over here. So what we have therefore will be, or probably we call this x square. Yeah. So it's gm rho dx, so that it's aligned with the symbol that we're using, x square. Yeah. So this is the gravitational force on that small little mass. Now if you want to find the total force on this mass, we have to sum it up. So therefore we integrate force from 0 to F equals to integral gm rho dx over x square. From the distance is from 2r to 2r plus L, where this length over here is L. So this section over here, you have F, which is equals to minus gm rho upon x from 2r to 2r plus L. So we have gm rho 1 upon 2r minus 1 upon 2r plus L. So if you common denominator it, it will become 2r plus L, and this will be L. Now what is rho times L? Isn't it the mass of that small little object, that rod over there? So it will become gmm upon 2r plus L. Now does this answer make sense? Take a look. What happens when L goes to 0? That means the rod's length goes to 0. Now if the rod's length goes to 0, it means that the rod becomes a point mass. When the rod becomes a point mass, it means that L goes to 0, and therefore it should go back to the equation that we learned about, which is gmm upon r square. And it does, because if you take a look at this, gmm upon 2r times 2r plus L, and the L goes to 0. Now that means that you have an expression of gmm upon 2r whole thing bracket square, which is actually this form. So it makes sense, and you always need to check when you get an expression for a special case, see whether it reduces to something if you are familiar with when you set the parameters to certain extremes. In this case, when L equals to 0, then you should have the expression there. Alright, so this is how the, I'm not focusing so much on the integration, but the method that to set up the integral. The small little force, how do you write the expression for the small little force using the small little mass and converting it to dx. Alright, so the next thing I'm going to go to is this, this other question, similar, but I wouldn't say slightly different. All I'm doing over here is to twist the rod such that it looks like this. Let's put this as L and L. So Obviously, the rod will be attracted towards the mass, the star, but the question is, what is the collective attractive force? Now, you have noticed that the force over here and the force over here, the vertical components will cancel out. So only the horizontal component will add up due to this small little f. So let's write an expression. Let's call this, okay, it's kind of a little bit weird that we call this x, but let's call this x. So what we have over here is that the df expression is therefore gm dm divided by r squared, which is actually equals to gm, the same rho dx, which is a small distance x over here, divided by this distance square, which is actually x squared plus 2r squared. That's it. All right, so what we have here is df, but what we want is not df. What we want is df cosine theta. Where is theta? So it is a horizontal component, remember, that adds up. So if you take 2 times, why 2 times? Because there's a horizontal component here due to this force, and there is a horizontal component due to this force. Therefore, 2 df cos theta will become 2 gm rho upon x squared plus 2r squared. Now, how do you come out with the expression for cosine theta? You take adjacent over hypotenuse. Therefore, you take 2r divided by 2r squared plus x squared square root, which will end up with 4 gm rho r divided by x squared plus 2r squared to the power of 3 upon 2. All right. Now, it doesn't look that friendly, and yes, it is not that friendly. So if you integrate 2df cos theta, you will end up with integral of 4 gm rho r divided by x squared plus 2r squared to the power of 3 upon 2 dx. I forgot to put a dx here. Cool. So this collection over here will give you the f. And the integral that you should go from is 0 to L. Why not minus L to L? Because I've already factored in the 2 over here. That means I factored in the other side. So therefore, I don't need to go from minus L to L. I just need to go from 0 to L. So if I want to go from minus L to L, then you should actually substitute just without the 2, just 2 over here. All right? So now, at this point in time, I need to introduce to you a standard integral where it looks like this. The standard integral is that if you've got anything that's integral of 1 upon square root of x squared plus a squared to the power of 3, this will become x over a squared x squared plus a squared square root. So let's try to get this in this form. So you got 4 gm rho r, that's the constants. This will be integral from 0 to L, 1 upon x squared plus 2r squared to the power of 3 dx. So as you can see, this is actually this form over here, just that the a is your 2r. So the standard integral is 4 gm rho r x upon a squared, 2r times x squared plus 2r squared and square root, and this will go from 0 to L. Okay, and we know that when you substitute 0 into here, it will be 0 throughout, so it will only be the L that is important that's substituted here. So this will give you 4 gm rho, if you substitute L in, will be RL divided by, probably R put over here, 2R L squared plus 4R squared square root. Still okay? Right, let's take a look. So therefore, what we have here is 4gm rho L R divided by 2R L squared plus 4R squared square root. Now again, rho L, 2 rho L will be equals to the mass. So it will be 2gm m upon 2gm r divided by r cancels out, so you don't have an r here, and you got the 2 here cancel out as well. So therefore it will be this. Right. Turns out to be a rather simple expression. Now the interesting thing is that when you, same thing, when you put L to be equals to 0, then you actually go back to your usual expression of gmm 1r squared. Okay? Hang on, there's something, seems to be something, let's check. Something is missing. Let's do a more rigorous check. You got 2r, you got r there. Because this one reduces to 2r. So did we miss out anything? Let's do a check on the integral. So you got this. Yep. 4 gmm rho r equals to this. 3 square root, and you got your x upon 2r, this one. Suspect that it could be here. Could it be 2r divided by this? Half cosine. Yep, that's correct. Looks fine. So then you got your 2r. Is there a 2r squared? 2r squared square root. Ah, right, sorry, it's a squared, not a. Make a mistake over here. There should be an integral over here that this should be squared. So if you cancel away 2r squared, you should have a 2r remaining. So there should be a 2r factor. And that is correct already, because if that's the case, when L goes to 0, this becomes 2r, and therefore this becomes 2r. 2r times 2r, it gives you 4r squared. So it's correct. Just that when I wrote the integral down, I forgot I wrote it as 2r instead of 2r squared. Alright, so this is basically how you get the expression for if you have a rod tilted at right angles to the line joining the center of masses. Okay. So how do you deal with energy? But before we even begin with energy, you will learn part of it in your topic 10. Probably I will give you a kind of induction. So kind of like teaching you topic 10 before topic 10. So let's take a look at the energy portion. Now let's start with basic principle. The basic principle is that any work done will result in a change in GPE plus a change in KE. Now imagine a scenario where I have this R over here, or rather, it doesn't matter. If I got a mass M over here, there's a point over here, and this distance is R, and this point we call it infinity. Infinity is basically a fictitious point where it's very, very far away, where the gravitational pull is negligible. So if I bring a mass from infinity to point X, somewhere along the way, I bring it across in this direction at a constant speed. I bring it in such a way where it's constant speed. So in order to bring it at constant speed, I need to exert an external force that's equal and opposite to the gravitational force. So the external force is this way. Gravitational force is this way. And the work done that I do is going to be equals to F external times the small little distance that I move cosine theta. And the cosine theta over here is going to be cosine 180 degrees, because this and this distance move is going to be at 180 degrees, which will give me minus F external dr. However, F external is equals to negative of Fg. So this will give you Fg dr. Now, do you agree that work done must result in a change in GPE and KE? Since V is constant, there is no change in KE, and therefore there's only a small change in GPE. So this becomes a change in gravitational potential energy. Hence, if du is equals to gmm upon r squared dr, and I integrate this from 0 potential energy at infinity to a certain potential energy at distance R, I'll get U equals to minus, and this is the potential energy of a mass at a certain distance. Alright, so this is the expression for potential energy, not mgh. Mgh is the change in GBE. Remember that. It is a change in GBE, not GB. So how do you apply this equation to the situations that we do just now? So how do you find the potential energy of a rod? R, and L. Same method. You consider the potential energy of a small mass, dm, or dx, having mass dm. So the small little potential energy of the small little mass will be equals to negative g, big mass m, small little mass, because it's mass per unit length times the dx, divided by the distance from here to here. So let's call this x. Yeah. So if you integrate this from, this x will be from 2r to 2r plus L. This will be 0 to u. So u will be equals to minus gm rho integral of dx x 2r plus L. This will give you minus gm rho ln x from 2r to 2r plus L. Now this will give you potential energy equals to minus gm rho ln 2r plus L upon 2r, which is minus gm rho ln of 1 plus L upon 2r. So that's the potential energy of the system. All right. Cool. Now, when the length becomes really, really small, this is where you need to know a little bit of mathematical approximation. You need to know that ln 1 plus x is approximately equals to x for small x. So therefore, if the length is small, this will become 1 upon 2r. L upon 2r, sorry. Now, how does this work out? If you take this to be the mass of the small little object, isn't it the expression that we learned previously? Minus gmm upon the distance. So what happens is that this L over here becomes really small. All right. So that's how we work things out for the energy of a small little rod. Now, how do you work out the energy of a rod placed in a position that we have gone through just now? The one where it becomes vertical. So the same situation. L, how do you work out the potential energy of this object? So u du, the small little mass over here, is equals to minus gm dm upon, this is going to be 2r squared plus x squared square root. Potential energy is a scalar quantity. There is no vector addition, so you don't need to care about the direction. So just sum up the potential energy. So if I were to integrate this from 0, or rather 0 to L, I multiply by 2. So from here to here, but it is symmetrical, so I just simply times 2. So this will give me u, which is 2gm integral of rho to L, rho dx upon square root 2r squared plus x squared. And this will give me, based on a standard integral, 2gm rho. Let's take a look at the standard integral. If you have this form, integral of 1 upon x squared plus a squared square root dx, it is equals to ln of x plus square root of x squared plus a squared. So following this, you have ln of x plus square root of x squared plus 4r squared square root, and it's from 0 to L. So 2gm rho ln of L plus square root of L squared plus 4r squared divided by, if you substitute x equals to 0, it will just be 2r. Is it correct? So 0, 0, so square root of 2, 4r squared becomes 2r, and you minus away, so it's divided by 2r. Correct. Cool. Right, so if your L approximates to 0, as you can see, I realized that I missed out a minus sign, minus sign, minus sign. Now if your L goes to 0, it actually goes back to the previous form as well. Let's take a look. So this one will become equals to 2g minus 2gm rho ln of, if L goes to approximately 0, you will have L squared, basically 0, divided by 2r, which is equals to minus gm rho ln of L upon 2r plus 1, which goes back to the formula that we are familiar with, L upon 2r. Rho L becomes mass, and you get gmm upon r. Yeah? So it's the same formula that we went through just now. All right. Okay. So therefore, this is the method that you go about solving the equation for the potential energy due to a rod placed at two ends, placed right angles. Now, the next thing that we're going to go to is basically the energy required to strip a planet apart, to dissociate the planet totally from, say for example, this planet over here. How do you find the energy required to just tear the planet totally apart, far from each other? So this is what we're going to do. All right. Okay, so what we have is, how do you tear the planet apart? You tear it layer by layer, like an onion. So if I were to strip this thing apart and pull it to infinity, so what will be the energy? So let's take a look at the energy of this shell. Now this shell has a small little energy of, no, not yet, minus g mass, say if the mass of this planet is m, times dm divided by r, which is gm upon r times 4 pi r squared dr times the density of the shell, which will give you minus g m 4 pi r dr rho. Now this is not the end. This m over here can be further broken down into g minus g 4/3 pi r cubed rho. Again, 4/3 pi r cubed rho, which is the mass of the planet, times rho dr, which is equals to minus, this is going to be extensive, 16 upon 3 g pi squared r4 rho squared dr. Alright, so if you integrate this, energy required from 0 to u, and this will be from 0 to r, this will be giving you u equals to minus 16 over 3 g pi squared r5 upon 5 rho squared from 0 to r, which is going to give you minus 16 upon 15. Hang on, the minus sign should go away. Let's see how we can take it away. Understand. So this is minus 16 upon 15 g pi squared r5 rho square. So this is the expression for the energy in order to rip all the whole planet apart into small little pieces. Now why is there a negative? That means that this is the potential energy of the whole planet. So in order for you to rip it apart, you need to supply this amount of energy to make it zero energy. Now let's do a final check and see whether this expression is fine. Quick check. dr divided by r, and so r squared cancel off. 4 pi r squared, 4 pi r, 4 pi r cube times rho times 4 pi, okay, and 16 upon 3 g pi squared r4 rho squared dr. Yeah, looks fine. Okay, so this is the expression for the energy to rip a planet apart. Definitely a big energy because this is r to the power 5. If you look at the radius of the Earth, that will be 6.4 times 10 to the power of 6 to the power of 5. Humongous energy. Even though this is minus 11 times this times 10 to the power of probably about 5,000 then per kg per meter cube. So it's still a very big number, which is expected. Now, lastly, I'd like to just go through quickly what's the orbital motion if it is elliptical. Now, if it is elliptical, you've got a mass over here and it goes like this and like this. This is called the perigee. This is called the apogee. These are the names given to it. And this is R perigee, this is R apogee. Now let's take a look at the equations involved in this motion. Energy is conserved. So at the perigee, the total energy will be gmm upon R perigee plus half m of the orbiting satellite times v perigee square must be equals to at the apogee minus gmm upon R apogee plus half mv apogee square. So that's the conservation of energy. It must obey. Now there's one more thing that it has to obey, which is the conservation of angular momentum. Now, remember we went through the last lesson that angular momentum is conserved if there's no torque. Remember that if F equals to dp dt, if net force is 0, momentum is conserved. Now, if torque is equals to dl dt, L being the angular momentum, if torque is 0, then angular momentum is conserved. So if you take moment about this point, can you see that all the forces always point towards the mass over here, which means that the torque is 0. So if you take the angular momentum with reference to this position, it means that the angular momentum is conserved. And still remember that angular momentum is equals to mvr. Just be careful that the v has to be the v perpendicular to the r. In this case, at these 2 points, the v is perpendicular to the r. So we can say that mv apogee, perigee rather, r perigee is equals to mv apogee, r apogee. M can cancel off. So all you need to do is, what you can do is, say for example, you want to make the v apogee as the subject. So you eliminate Vp, which is equals to VA RA divided by Rp, and then you can substitute Vp into the equation on top. So minus gmm upon Rp plus half m VA squared RA squared upon Rp squared equals to minus gmm upon Ra plus half m VA squared. Now if I make VA squared the subject, I can factorize this out, and this becomes 1 minus half mVA squared. This will be RA squared divided by RP squared equals to gmm. I bring it over the other side, and I can find the KE or whatever I want to find in terms of purely the distances. So I can find the KE or even the speed of the object at the apogee or the perigee, so long as I know the RA and RP. So this is a very useful equation. I suspect that you might not be able to see this, so let me tilt this a little bit so they can see the expression over there. So this is the expression for the perigee and apogee's velocity. All right. Okay. So one question I'd like you to leave with you to think about and to find the expression for is this. I'd like you to think about this. If I were to have a object, say this is R, and I launch it at the angle V, this is M, small little mass M, it will travel out before it strikes again. So the question is, what's the maximum height h that it reaches before it comes around and strikes Earth again? So this is the question I'd like you to think about, and let's discuss this in the next lesson. All right? So I'll stop here. Thank you for listening to this lesson, and hopefully you learned something that is useful for you. Thank you.